In the last video, we took our definitions of position, velocity, and acceleration and extended them to two dimensions. And what we saw in that was that actually nothing really changed except we put little vector signs over things. And since all the mathematical operations involved, like finding a change in position or change in velocity, involved adding and subtracting two vectors. If you think about that, what you're going to be doing is adding or subtract. You're going to be subtracting the x components and the y components separately. Then the only other thing you're doing is multiplying by 1 over delta t, which is multiplication by a scalar, which that happens across both components. So fun little tidbit with this is that no x component information will ever work its way into a y component in a calculation or vice versa. So the upshot is that you actually end up with two complete gangs of four. One for the x component of the motion and one for the y component of the motion. So I like to call this the land of x and the land of y. And I like to imagine that there is a great big wall between the land of x and the land of y where nothing gets passed back and forth. You do not pass x and y components of velocity back and forth. You don't pass x and y components of acceleration back and forth. You don't pass x and y components of position back and forth. But like with all big walls, somebody usually gets around to digging a tunnel under it. And the bit of information that can get traded back and forth between the land of x and the land of y is the time. So if you're ever solving a y equation of motion, you can solve for the time in y and then stick it over into the land of x, or vice versa. You can solve for the time in the land of x and move it over to the land of y. But that's as far as you can go with that. But otherwise, you just treat this like when you do motion two dimensions, you treat it like you are simultaneously solving two one-dimensional motion problems. So I think this is probably easiest done just working by example here. So let's go ahead and do a couple examples. So let's say you are on the top of a cliff. Like so. There you are. And you're going to throw a ball off the cliff. And let's say you launch it at 5 meters per second, purely in the x direction. So we can go ahead and say v initial x is 5 meters per second. V initial y is 0 meters per second, because you're working purely, because it was thrown purely in the x direction. Okay. In fact, just to make it clear, let's just go ahead and draw in a coordinate system, just so we're very clear about what is x and what is y. So this is the plus x direction. That's the plus y direction. Okay, so after you throw the ball horizontally initially like that, we wait 2 seconds. And what I want to know is after 2 seconds, how fast is it going? Well, we can finish out the picture a little bit here. It'll turn out that the path this thing takes is a parabola. And so what we're really asking for is what is the magnitude of the velocity vector. Our strategy here is going to be to separately find the y and the x components of the velocity, and then we will use the Pythagorean theorem to put it back together. All right, so we've identified what we need. We need to find Vx and Vy so we can find V. We're given V initial, we're given 2 seconds. We need at least one more piece of information. Oh yeah, right, we're on the Earth. So we know that the acceleration is going to be straight downward. So we can write that a sub y is minus 9.8 meters per second squared, and a sub x is equal to 0 meters per second squared. All right. So when we do these things, I always like to keep the land of x and the land of y separate, unless I have to trade the time between them. But here I don't need to. I know it's 2 seconds. So we can start in the land of x. We're trying to find what Vx is equal to. And we realize that what we're missing is x, the final position. So we can use the missing x equation to say V final x. I should say V final, V final, V final, V final there. V final x is equal to V initial x plus a sub x delta t. Well, a sub x is 0. We're always allowed to stick in 0 right away, so let's do that. So we get that V final, the x component of the final velocity is the same as the initial. So it's 5 meters per second. All right. Now let's go over to the land of y. So again, same deal. We want to find Vy. Again, here we are neither asked for nor given the y coordinate, so that's missing. So again, V final y equals V initial y plus ay delta t. Well, V initial y, since the ball is thrown purely horizontally, V initial y is 0. So we can put that in right away. And then we can put in that a sub y is minus 9.8 meters per second squared times 2 seconds will give us negative 19.6 meters per second. Now what we wanted was the final speed, so we can go ahead and put those together. We can do that by recognizing that our components are going to form the legs of a 3, 4, 5, or sorry, of a right triangle. Form the legs of a right triangle, not necessarily 3, 4, 5. In fact, it won't be. Vy is negative 19.6 meters per second. Vx is 5 meters per second. So my velocity, we could work out the angle if we were so inclined, but we were not asked for that. So you just know the velocity does one of those numbers. So V squared will be equal to Vx squared plus Vy squared by the Pythagorean theorem, since that's a right angle right there. You can take the square root of both sides. Get that V is the square root of Vx squared plus Vy squared. And sorry, again, I should be putting finals everywhere. There we go. So you get that V final will be the square root of 5 meters per second squared plus negative 19.6 meters per second squared. And again, we're not fussed about the minus sign because we're going to be squaring it. All right, do the units work. I'm going to have meters per second, which I squared that. I'll have meters squared per second squared. Ditto here, so when I add them, I'll have meters squared per second squared. And then I'll take the square root of both sides of that, so I'll be left with meters per second. So yes, the units do check, and I get 20.2 meters per second, which seems reasonable. If something's been falling for 2 seconds, it'll probably be moving pretty quick. All right. So let's do maybe a little more complicated problem. As I'm sure you all realize, based on the name of my channel, theta The FIDA in the name of my channel is an acronym. It stands for Federación Internacional de Tir al Arco, which is before everything got rebranded a few years ago to use the English names. That was the official name of the world archery, the International Archery Federation, now called World Archery. So I think we can take as a given that the most awesome and extreme of all possible sports is, of course, target archery. But we don't always have to be shooting at a target. In fact, there is a discipline in archery called flight shooting. In flight shooting, what the archer is endeavoring to do is just shoot for distance. And almost certainly wearing a hat so that they're not being fried out by the sun. There we go. So let's, just to make life a little easier, we'll ignore the fact that the arrow is going to be launched about a meter above the ground. And we'll just say that the initial position of the arrow is on the ground. Now let's say this particular archer, in an attempt to shoot for distance, like I said, is a discipline called flight shooting, so it is a legit thing, shoots their arrow at an initial velocity of 60 meters per second, which is a typical speed for a competitive shooter, an angle of, sorry for the bad art, 30 degrees. This is probably not going to be a winning shot, but, hey, we can try. And so we want to know how far is it going to go before it hits the ground. All right. So if we go ahead and say that x initial here is 0, what we're really asking for is, what is x final? All right. So what else do we know about this? Well, as awesome as it would be to have archery competitions on other planets, we're not there yet, so we can probably assume that this competition is being held on Earth. So if we go ahead and choose this to be the plus y direction, that to be the plus x direction, we know that the acceleration is going to be straight down, so we can say that a sub x is 0 meters per second squared, and a sub y is minus 9.8 meters per second squared. Do we know anything else? Yeah, actually we do. We know the final height of the arrow. We know it's also 0 when it hits the ground. So now we've pretty much put down everything we know. The only other thing that will be useful for us is to break our initial velocity into components, because when we go into the land of x and the land of y, we will want v initial x and v initial y. So we can just draw that out real quick. So this is my v initial, which was 60 meters per second. There's my angle theta, which is 30 degrees. So v initial x here will be v initial. Now, just ask yourself for a second, am I going to want to multiply by sine, cosine, or tangent of 30? Pause and we'll get back. Okay, that'll be the cosine, because the x component here is the adjacent and I have the hypotenuse. And similarly, we can write that v initial y is v initial. We're looking for the opposite, so it'd be sine theta. Okay, so I have everything now. So let's just start. We'll do this uncleverly just to show a thing that might happen. Sometimes what might happen is that you discover that you don't have enough information, or that the information you have isn't useful enough. So since we're asking for x final, it would probably be reasonable to just start our problem in the land of x and assume that that will take us there. It won't be quite good enough. But if we look at this, we can say, well, we know v initial x. All right. We don't, well, let's see. We don't know the time of flight. We weren't given the time of flight. So you might be inclined to say, okay, let's try using the missing delta t equation, right? Well, if you do that, what are you going to get? V final x squared equals v initial x squared plus 2a sub x times x final minus x initial. All right, x initial, we can put that in for 0. Looking good so far. So we can solve this for x final. And I'll just jump ahead and do the algebra and assert that when you do the algebra, you're going to get that x final is vx squared minus, v final x squared minus v initial x squared over 2a sub x. But here's the problem. When you put in the numbers, that's a 0. So you're dividing by 0, which you're probably not too happy about that. So that ain't gonna work. So now you do realize that if you thought about it a little bit longer, you realize that you were in a pickle anyway, because you are also missing v final x, right? We don't officially know this. Now, if we put in that this is 0, we get that it's the same thing, but we don't officially know it, and even if we did, it wouldn't help us. So we could go ahead and so to get our distance, since we're missing v final x, let's actually legit use that. And we're going to see that we're still going to be in trouble. So this is going to give me that x final equals x initial. Okay, x initial is 0. I can put that in right away. Plus v initial x delta t. So far, so good. Plus 1/2 ax delta t squared. And hey, ax is 0, so that's all good, right? Except we don't know delta t. That wasn't given to us either in our problem. But when this sort of thing happens, you don't have to despair. If you don't have enough information, this was really the issue. If we were more careful, we would have realized that we were missing 2 variables. We were missing vfx and we were missing delta t. And you can only be missing 1. So if you're missing 2 of them, then it turns out that it'll always be the case, if you're missing 2 of them, that one of them is the time. And then if you are stuck in the land of y, for instance, you could go to the land of x to solve for the time. Here, we're stuck in the land of x. So this means we need to go to the land of y to solve for the time of flight. So once we get the time of flight in the land of y, the strategy will be to take our solution and stick it back in to where we're stuck right here to get our delta t to finish off the problem. All right. Well, it's still the case that it turns out we're missing v f sub y as well. You might want to pause for just a moment and ask yourself, why don't we know it? I mean, isn't it 0? The answer is no, it's not 0. This is a subtlety that you have to be careful about in kinematics. And that is that we know that just before you hit the ground, the arrow was definitely moving, and then it hit the ground. Well, in order to scrub off all that y component of velocity, you have had to have had a massive upward acceleration on the arrow to bring it to a stop vertically. So a sub y turns out will be a very large positive number, much bigger than 9.8 by like a lot. And the problem is we don't know what that number is, and we don't know how long you're in contact with the ground. So what you have to, but the problem is that since that's a different acceleration, even if we knew it, it would still be a problem. Since it's a different acceleration, that means that that violates our assumption of constant acceleration that kinematics relies on. So the usual cheat we do in situations like this is we look at the whole thing just before impact. I mean, like as close to before impact as you want, so that, you know, the height is really, that you're looking at is like really 0.000000001, and you just approximate that to 0 or whatever, it doesn't matter. But the point is that just before impact, we don't know what V final is. It's something, but we don't know what it is. We could solve for it if we want, but we don't need it. So we'll use the missing V final Y. That will be Y final equals Y initial plus V initial Y delta T plus 1/2 AY delta T squared. All right, thank God for small favors. We can put in zeros for Y initial and Y final. And so what we're left with is 0 equals V naught Y delta T plus 1/2 AY delta T squared, and we're solving for delta T. So this is probably giving us some flashbacks here, but this is probably about as awful as it gets for having to solve for the time. And you could, if you want to, just go for the quadratic formula here, plug it, grind it, it will work for you. But before we run into that, we can take a look and say, hey, since there are no constants here in this particular case, it's actually really straightforward to just factor this, so let's factor it. So we get that 0 equals delta T times the quantity V naught Y plus 1/2 AY delta T. And we remember from our algebra classes that this is 0, that will get 0 one of two ways. Either the thing I did in red is 0, or the thing I did in purple is 0. So the thing I did in red would give us delta T equals 0, which, while true, isn't useful. The reason it's not useful is delta T equals 0 corresponds to when I shot the arrow. So yeah, we know that times 0 is at height 0, because I gave us that little cheat to make the math easier. So we know at times 0, the height is 0. That it's a true statement, but it's not useful. So we have to solve the other one here for the time of flight. So we can do that. Well, let's see, V naught Y plus 1/2 AY delta T equals 0. So 1/2 AY delta T equals minus V naught Y. Sorry, not V naught, V initial. My bad. So, right, and V initials there and there. My apologies. All right. So then we get that delta T is equal to minus V initial Y. Let's see, we get multiply both sides by 2, divide by AY. Cool. Now, you might be freaked for a moment and say, hey, wait a minute, that's negative. If you rejected delta t equals 0, surely you must be rejecting something negative, right? I mean, that's before 0. So, if 0 is bad enough, wouldn't we want to reject before 0? So pause and ask yourself why this is okay before we move on. Okay, the reason it's okay is that a sub y is negative. Remember, a sub y is negative 9.8 meters per second squared. So I have a minus and a minus, so it turns out that this is still positive, so life is good. All right, so now, while in general we're never allowed to travel between the land of X and the land of Y, we can always dig a little tunnel to move the time from one land to the other. So this is what we need. So now we can finally go back to solving for X final. So X final will equal, well, we have a V initial X, then bringing in all the rest of the stuff, we have a minus 2, a V initial Y, and an A sub Y. Okay, and we remember that V initial X was V initial cosine theta. V initial Y was V initial sine theta. So if we clean it up and make it all pretty and everything, we get that X final equals minus 2 V initial squared sine theta cosine theta over A sub Y. Now, if you want to go, there are trig identities you can do to make this prettier, but at this point, I'd say I'm happy. So let's just go and stick everything in. So this will be minus 2 times 60 meters per second squared sine 30 cosine 30 over negative 9.8 meters per second squared. All right, so first off, the minus signs cancel and I get that X is positive. That is important as a sanity check. The other thing we need to check is do the units work. Well, in the numerator, we have meters per second, but then I'm going to square it. So they'll square both the meter and the second. So the numerator is in meters squared over seconds squared. They'll be divided by meters per second squared. So the second squareds cancel and 1 power meters cancels, leaving me with just meters. So that works as well. So this will give you X final is equal to 318 meters. So you can ask yourself, is this reasonable? And the first thing that you would look at is you'd say, well, it's a positive number. That's good. I would hope that the archer shot it downrange. That it's usually really bad if you shoot an arrow in the other direction. And then you ask yourself, 318 meters. Well, the archer is trying to shoot for distance. So is this a legit number? And while you may not remember off the top of your head that the world record for flight shooting is actually, a little over a mile. So that this would be kind of short for that, but I didn't say the archer was doing a good job. Certainly for a shoot for distance kind of thing, you can remember from, when last time you watched archery in the Olympics coverage, you know that the shoot down matches are always contested at 70 meters. And those are archers who are trying to shoot for accuracy. So if 70 meters seems like a reasonable distance to be shooting for accuracy, if you're just plain letting her rip, 318 meters seems reasonable. You can think about, so that's maybe about 3.5 football fields. That seems plausible. So all in all, the number seems pretty good. Now, I will end this with one more cautionary tale. Before you go and say to me, hey, couldn't we have used the range equation? If you have ever heard of the range equation in some previous lifetime, I strongly, strongly, strongly urge you, as best as possible, to try to put the range equation out of your mind. Why is this? That's because if you have encountered this beast, it is only valid for shooting over flat ground. So remember this problem here. In order to make things easier, I had said, let's assume that the arrow got launched from the ground. But in reality, the arrow is going to be something like 1.5 meters off the ground, something like that. So if you're going to be doing this more carefully, that's something you could not ignore. And then that means you couldn't stick in 0 for y initial, and that will be all you need to ruin that range equation. So again, here, this is me saying that I'm generally a fan of start with things that are always true and apply them to the specific circumstance. If you have equations that are only valid for a specific thing, the danger is that they could look like they have all the right variables, but it's not actually the right equation for that exact situation. So for instance, if I were to do this again, not neglecting the initial height of the arrow, we would get a different answer. It would be actually a little further down range. Or say if we were rethinking history and thinking of the Battle of Agincourt, where you had archers on top of a cliff, well, then definitely there's no way you could pretend that the initial height of the arrows was 0, and then those range equations definitely wouldn't work. So, alrighty. So, have fun, and I will catch you on the flip side.